Okay, you have any questions on past material? Okay, right, today we're going to take a look at higher order tries, and this will be our last lecture on the trie data structure. So far, we have looked only at binary tries, and as you might expect, the height of binary tries could be large because you're only doing two-way branching. Okay. And when the height is large, that in turn means that when you do a search, you have the potential for a large number of cache misses. Similarly, when you do an insert or delete. By going to a higher order trie, perhaps by performing, let's say, 10-way branching or 100-way branching or 1,000-way branching, we can reduce the height and thereby also reduce the number of cache misses that take place, and so improve performance. Okay. All right, so let's take a look at an example. Let's suppose we're building a dictionary structure for an environment where the keys are social security numbers. Okay, so we have a large number of customers and they're being keyed in by their social security number. The social security number we know is a 9-digit number. So for example, this could be a potential social security number for someone, 9 decimal digits. Okay. Now, if we did 10-way branching, which means each branch node has a degree that is 10, okay, then the branch nodes of our trie would look something like this. If the digit you're looking at is a 0, you go into that subtrie. If it's a 3, you go into this subtrie. If it's a 9, you go into that subtrie. Okay. So in 10-way branching, we would examine the digits in the key left to right using a base 10 decomposition of the key. Okay. We could certainly set up a binary trie with the same key. Then we'd do a 2-way branching using a base 2 decomposition of the key. So using a base 10 decomposition, at the root level, we'd branch on the first decimal digit, in this case of 4. Then at the next level, we look at the next decimal digit and so on. Okay. So our branch nodes would have 10 child fields in them. So depending upon whether the digit you're looking at is a 0 or 9, any one of these numbers, you would go into the appropriate subtrie. Okay. When you reach a situation where a subtrie has only one key in it, then you would place an element node over there. Okay. So we could do 10-way branching. That would give us an order 10 trie. Okay. In this case, the height of our trie could be as much as 10. Okay. So we could be doing let's see, so if we have a 10-way trie, the height could be as much as 10, which means you could have 9 levels of branch nodes for each of the 9 digits in our social security key, and then you have 1 level of element nodes. So if you're performing a search, we may end up looking at all 9 of the decimal digits before we end up at an element node. And so you could move down 10 levels of nodes, which in turn would mean that you would have at most 10 cache misses during a search. Okay. Right. So with 10-way branching, we could have up to 10 cache misses. Okay. Now, to get a feel for why it is 10 and not bigger, because this is going to be important when you look at higher order tries. Let's go back at this picture here. Okay. All right, so if you look at this picture here, if you think about the node getting very large, then certainly you can't read the whole node in with one cache miss. It's not going to fit into a cache line. Okay. So if you have to read the whole node in, that potentially could involve many cache misses. Okay. Now the nice thing about tries is that you don't need the whole node to be read in. Okay. So for example, if I know that my digit is 4, then all I need is this pointer. Okay. And if this thing is set up right, for example, now let's think of this as an array. Okay. Then I don't need to get position 0 through 9 of this array. I only need to get position 4 of the array. And I can get position 4 of the array with a single cache miss, regardless of how large this array is. Okay. So if the node is set up as an array, it doesn't really matter how big the node is. At every level, we only need a small part of the node, and we know which part, and we can get that part by having a single cache miss. Okay. Now, if we went to a 100-way try, sure, the nodes are going to get bigger. Each branch node will have 100 pointers in it. Okay. But with the same 9-digit key, okay, at the root level, we would branch using the first 2 digits. At the next level, we'd look at the next 2 digits, then at level 3, the next 2, at level 4, those 2, and at level 5, we would have only 1 digit to look at. Okay. So in the case of a 100-way try, our height would be at most 6. 5 levels of branch nodes. The first 4 would be 100-way, and the last one could only be a 10-way. And then you would have an element node also in the picture. So you could have up to 5 levels of branch nodes on any path, and then 1 element node. Okay. So you would do up to 5 branches on your way down, followed by a single compare at the end, where you would compare this 9-digit key with whatever's sitting in the element node you reach. If you compare this with using, say, some of the balance structures we've seen. If you look at a red-black tree, well, the height of a red-black tree, if you take this thing to an extreme and you assume you've got all potential billion Social Security numbers in use. Okay, so you've got 10 to the 9 different numbers. Okay, so if you assume that all 10 to the 9 are in use, then your height could be as much as 2 times log of n, okay, which means you could have 60 levels of nodes. Okay. And what that means is that to find what you're looking for, you could perform up to 60 comparisons of 9-digit numbers. Okay. Using a try, there is only 1 comparison. So it doesn't really matter how big the key is, because you're only going to do that compare once. You do a lot of digit extraction, okay, but you can extract digits in constant time. Doesn't really matter how big the thing is that you're extracting the digits from, okay, especially if you choose your radixes right. Okay. And so here we're looking at doing maybe up to 60 compares of large numbers. Whereas if you had a 100-way try, we would do at most 5 branches followed by 1 compare. Okay. So far fewer cache misses and far fewer compares. Okay. If you used an AVL tree, then the height could be as much as 40. Okay. And that means up to 40 compares. Okay. But it also means up to 40 cache misses. If you use the best binary tree, so that would be a full binary tree or a complete binary tree, you're at about 30 levels. Okay. Certainly you can bring this number down. You can go to red-black trees and things. But when you're talking about, I'm sorry, not red-black, but B trees. Okay. But when you're talking about B trees, as you get to larger nodes, the number of cache misses per node goes up, because you do have to read that whole node in to figure out which subtree to go into. Okay. Unlike a try, where you only need to read in the particular pointer that you need to move down, in the case of B trees, because you have to perform a binary search inside the node to determine which subtree to move, you potentially need that whole node in. All right, so so high degree tries have a lot of potential for dictionary applications. It's a they represent a very simple structure. There's really no active balancing technique that's employed there, and yet they provide very good performance in the right kind of application. Now, in the same Social Security application, if we went through and said, well, I don't really have close to that billion, but I have only 500 keys. Well, even with 500 keys, our trie could have the maximum possible height. Whereas in the case of an AVL, we're looking at log of 500 base 2. Okay. So those structures, if you get small enough, they will do a lot better than a trie would do. Okay. You got to have reasonable population of the space. Okay. All right, let's take a look at a compressed Social Security trie. Okay. The node structure that we'll employ, assuming that you have 10-way branching, okay. A branch node will have 10 child pointers, one for each of the possible values for the digit you're branching on. You'll have a character number. Okay. It tells you which character or digit of the key you're branching on. Okay. So this is equivalent to the bit number field that was being used in a compressed binary trie. Okay. Then we have this field here that we didn't have before, which tells us the number of non-null pointers in the node. Okay. This is going to be useful when we perform a deletion, because a property of a compressed trie, whether it's binary or otherwise, is that each branch node must have at least 2 non-null pointers in it. Okay. So using this field here, we can keep track of how many non-null pointers there are, and every time you remove one, we can decrease this count by 1. Every time you add in one, you can increase this count by 1. And when the count drops below 2, it's time to get rid of the branch node. Okay. So the structure is somewhat similar to what's used in compressed binary tries, except that here we're keeping track of the number of pointers to avoid having to count how many non-null pointers there are every time you do a delete. Okay. Well, let's take a look at the insert and delete operations. As we'll see, these are just a natural extension of the ones discussed earlier for compressed binary tries. All right, let's suppose we start with this particular key. Okay. And we're going to build a 10-way compressed trie. Okay. So we start with an empty trie. We're going to insert this key in it. We're going to end up with one element node. Okay. Again, we have the same relationship here with respect to well, I guess it's really not the same, but if you have only one element, then there will be no branch node. The requirement is that every branch node must be the root of a trie that has at least 2 elements in it. Of course, a branch node could be the root of a trie that has many elements in it. Okay. So, for example, if you had 10 elements, it's possible that you have only one branch node, because the branch node has 10 pointers, and each of these 10 pointers could go to an element node. Okay. All right, so here we're starting with an empty trie. You get one element, and we just create a trie that has a single element node in it, which contains the key, and of course associated with the key there will generally be other values too, but here we're going to show only the key. All right, now let's suppose we want to insert this. Well, then you're first going to search the trie to see if this is already there. So when you perform the search, in this case, we end up at this element node. Okay. When you end up at an element node, you compare the two to make sure they're different. Since they're different, you sample these two from left to right, finding the first digit where they differ. So in this case, the first digit is number 3. That's where this one's got a 2, that one's got a 5. So I'm going to introduce a branch node where the branching is done on character or digit 3. If it's a 2, you go down here. If it's a 5, you go down there. Okay. All right, the picture doesn't show the null pointers. We actually have 8 null pointers in this node. All right, next, let's suppose we're going to insert this particular key. Okay. Again, you perform a search. You need to first look at digit 3. So you extract digit 3, which is a 5. So you branch on that. You end up at an element node. You compare the two. They're different. You find the first digit where they differ. So you scan left to right. So 1501523 agree they differ out here. This is digit number 6. Okay. All right, so having found out where they differ, you then need to know where to place the appropriate branch node. As was the case for binary tries, the digit numbers has to increase on the way down. Okay. So you're going to place the new branch node on the search path in such a manner that these digit numbers are increasing, so you're going to have to place it over here. Okay. So I break that link, put in a branch node on digit 6, and if digit 6 is a 1, you end up here. If it's a 4, you end up down there. All right, the next insert is going to be for a fellow with this key. Okay. You perform a search. You first look at digit 3, which is a 9. Okay. So you're going to branch on 9. 9 is a null. Okay. So you find nothing. Okay. When you end up at a null position, from wherever you fall off, you back up to the appropriate branch node, which is the branch node you fell off of, and you follow any path downwards trying to find an element. Okay. It doesn't matter which element you find, okay, because all of those elements agree on the first so many bits. Okay. Okay, so from here we find a path going downwards. Okay. And let's suppose you end up over here. Well, then you sample these two. Okay. It doesn't matter which one you get to. We know that when you sample, the first place they differ is going to be smaller than the digit number where you fell off, because you had a null out there. Okay. All right, so we sample, and in this case you find that this differs from that at position 2. Okay, this is a 7, that's a 1. Okay. And that would be, same would be true if you'd come here or there. So you're going to have to branch on character or digit 2, and that's going to happen before you reach this node here, so you're going to have to put up a node over there. Okay, so you do a digit 2 branching. Okay. All right, next, let's suppose we get this fellow. So you perform a search. So you first look at digit 2, which is a 1, so you end up here. Then you look at digit 3, which is a 2, so you end up here. Okay. You compare the two, they're different. Find the first place where they differ. So they agree on 0, 1, 2, 3, 4, 5, 6, and they differ out here, and that's number 8. Okay, digit 8. Okay. So we're going to put a digit 8 branch on this path. And it has to be done so that they're in ascending order, so you'll need to put it here by breaking this link. Okay. Right, so we get a digit 8 branch here. All right, we do yet another one. So we insert this fellow, do a search. You first look at digit 2, which is a 1, so you come here. You look at digit 3, which is a 1, so you fall off. The 1 pointer is a null. Okay. So at this point, you find anybody in this search tree here. Okay. So all of them agree on the first 2 digits, which is 0 and 1. So let's say you find somebody in this subtree. Maybe you find this guy here. Okay. You compare, and the place where you differ is digit 3. So you got a 2 there, and here you got a 1. Okay. So I'm going to be putting in a 1 branch over there. Okay. Whenever you fall off at a null, we know that you differ at least on the digit represented here, okay, and possibly on something earlier. So the first place where you differ cannot be something bigger than where you fell off. It either has to be the digit number where you fell off or something earlier. Okay. Okay. So the insert is pretty much the way you would do it for a compressed binary trie. Okay. Of course, when you do the insert, you have one added operation. You have to keep track of the number of pointers. So whenever you change a null pointer to non-null, you need to bump up the number of pointer count. Okay. Let's look at a delete. Okay. Again, delete is similar to how it would work for a compressed binary trie. You find what you're looking for in an element node. You throw away the element node. So, for example, if you want to delete this fellow, you perform a search and you find it here. Okay. So we're going to throw this node away, which means we're going to lose this pointer. Okay. Now, in the case of a compressed binary trie, when you lost a pointer, you know that the parent became deficient. It has only one non-null pointer. Okay. That's not necessarily true here. In fact, here we still have 2 non-null pointers. Okay. So to distinguish, we have that pointer field which tells us how many non-null pointers there are. Previously, that field had the number 3 in it. Now we drop it down to 2, which means this node survives. Okay. So in this case, we just throw this node away and change that pointer to null and decrement the count. All right, if you're deleting this fellow, you look for it and you find it here. So we get rid of that element node. A non-null pointer changes to null. The count for non-null pointers drops from 2 to 1, okay, which tells us that this node should also be dispensed with. Okay. So we're going to get rid of this node and just change the pointer from the parent to come here. Okay. You don't have to go any further than the grandparent. The grandparent's count doesn't change. Okay. Right, if you're removing this fellow, we perform a search and you find it here. Okay. So you get rid of that fellow. You look at the count in the parent. The count goes down by 1. If it becomes less than 2, then the parent has to disappear. Okay. But the grandparent count isn't going to change. It's going to be whatever it is. We had to change the pointer in the grandparent to come down here. Okay. And for that, you actually have to, if you're thinking of this as an array, you're going to have to search through the pointers to find out where that non-null pointer is in the node. All right, you have any questions about adapting the compressed binary insert and delete to the case of compressed higher order tries? Okay. All right, let's take a look at what we need to do if you're going to be working with variable length keys. The discussion so far has focused on fixed length keys. Okay. So suppose you had this particular trie, 10-way trie, and you're asked to insert 0, 1, 2, 3. Okay. So we would start here. We'd look at digit 3, which is a 2, so you'll end up over here. Okay. We'll compare the two keys. We'll find that they're different. And then my rule says find the leftmost digit where these two fellows differ. Well, there is no leftmost place where they differ. You run out, they agree, 0, 1, 2, 3 agrees with that, and then you got nothing else to look at. Okay. So you end up with a problem because the key that you're trying to insert here is a proper prefix of a key that exists. Okay. So whenever you have a key that's a proper prefix of another, then there is no leftmost place where the two differ. Okay. And to get around this problem, what you do is you append to each key a special digit, one that cannot normally arise inside of a key. So for example, here we say append this special character pound sign or marker, okay, to the end of every key. Okay. So you can think of this as 0, 1, 2, 3 marker. There's a marker, a pound sign sitting here, and one over here, and one over there. Okay. Once you do that, no key can be a proper prefix of another, because a pound sign cannot occur in the middle of a key. Okay. So that takes away the difficulty you have when you are dealing with variable length keys. Okay. Okay, so with that in mind then, we applied the same rule that we had earlier, okay, which is find the first place where these two differ. That's now going to be in digit 1, 2, 3, 4, 5. Because this one has a pound sign and this one has a 4 in that position. Okay. So I'm going to do a branching here on digit 5. Okay. So I do a branching on digit 5. If it's a 4, you get the old fellow. If it's a pound, you get the new guy. Okay. All right, so with this slight change to the keys, you can get the scheme to work for variable length keys. The scheme, of course, comes at a cost. Each node has one extra pointer field. Right, there are several variations on the basic trie structure. We'll run through some of them in class, and I'll let you look at the readings on the website for the remaining variations. In one variation, we augment our branch nodes so that each node has yet another field. This one we might call an element field. It points to one of the element nodes in the subtrie of which it is root. Okay. What this enables us to do is it enables us on the way down to find out what characters or digits are being skipped over. Which means that on the way down you could check for equality with these characters during a search. And if you find a mismatch, you don't have to go any further down the trie. Okay. All right, so we add a new field which points to any one of the elements in that subtrie. We use this information on the way down during a search to compare digits that you're skipping over. Right, so for example, if this is our 10-way trie, okay, then I'm going to augment each of my branch nodes. I haven't done that yet. Each branch node is going to be augmented. I'm going to give it another field called an element field. Okay. And this can point to any one of the element nodes in the subtrie of which it is root. Okay, so for example, this fellow could point here, but it could also have pointed there or here or here. Okay. This pointer would be used, for example, to extract digits 1 and 2. Okay. So on my way down, I come here, this says, well, branch on 3. Well, before branching on digit 3, I say, well, let me see if I've got a match on digits 1 and 2. Okay. Using this pointer, I can access this fellow and compare digits 1 and 2. If they don't agree, there's no point going further down. I'm not going to agree with anybody down here. Okay. So you can declare the search unsuccessful right here at this level. Okay. In this node, I could point to this fellow or to that fellow. Okay. Again, the idea is when you come here, before you branch on digit 5, okay, I can use this pointer to check out digit 4. Okay. So here I've already checked out digits 1 and 2. I've branched on digit 3, so I know there's a match on digit 3. I'm sorry, here. There's a match on digit 3. Everybody's got a 2. Then before branching on digit 5, I use this blue pointer here to check out digit 4, make sure there's a match. Okay. And so it doesn't matter whether you're pointing here or there, everybody has the same digit 4. Okay. So then once you verify that's true, then you actually do the branching on digit 5. Okay. All right, similarly here, we have a pointer to one of the two yellow nodes in its subtry. Okay. All right, so that's a variation that people employ to terminate unsuccessful searches early. All right, other useful pieces of information. If you're dealing with random keys, the expected height of an m-way trie is log of n base m. Okay. So without any effort at balancing, you expect to see a height that's about logarithmic. In practice, people might use one of two heuristics to control the height. One is to say that branching will be done only h levels deep. After that, all of the unresolved keys are placed into a bucket, and the bucket may be searched serially. So again, the expectation here is that after you've done, in this case, say 6 levels of branching, the sets of unresolved keys are small. Maybe you've got only 5 to 10 keys in each group, put them all into separate buckets, and then search those buckets serially. Along those lines, you may implement your heuristic slightly differently, which says you're going to keep branching until the number of elements in a subtrie becomes no more than some threshold s, let's say 10. So if a subtrie has only 10 or fewer elements, I'm going to stop branching. I'm going to stick a big element node there, a bucket which contains all of the unresolved keys. I'm going to search those serially. Okay. That's similar in spirit to the previous heuristic. Okay. So with this heuristic in place, the expected number of branch nodes, okay, total number of branch nodes, is expected to be something like n divided by s natural log of n. Okay. Some other things people do is instead of sampling the keys left to right, you may sample right to left, or you may sample in some random fashion using some pseudo-random number generator. Okay. So for example, if you have a dictionary of people's last names, and suppose that you have a large number of last names, like, well, it's not just last names, you've got people's names, so you've got a first name and a last name, but you're keying in first on the last name and then on the first name, and you've concatenated them. Okay. Well, then you may have a large number of people whose last name is Johnson, and so you may have to go through as many characters as correspond to Johnson before you have any hope of distinguishing. Okay. So to avoid situations like that where you expect long common prefixes in your keys, you may instead do it from right to left. Or if you expect a lot of commonality both in the front and the back, you might try some middle to out scheme. Or generally you might just try some random scheme to sample. Again, the idea is to reduce the number of levels of branching. A variation on high-order tries. In a high-order trie, as we have discussed it, you determine the order, say 10 or 100, and then every branch node has that order. Okay. A variation to that has been proposed for applications like IP routers, packet forwarding tables, and this variation is referred to as a multi-bit trie. Okay. So in a multi-bit trie, the degree of a branch node can change from one node to the next. Okay. So you assign to each branch node a stride. Okay. So each branch node gets assigned something we call a stride, and that determines the number of bits in the destination address of the packet that's used at that node for branching purposes. It also determines the number of pointers in the node. So if your stride is 1, only 1 bit is used, you can have 2 children. If your stride is 2, 2 bits from the destination address are used, you can have 4 children. Stride is 3, you use up 3 bits, the next 3 bits, and you have 8 children in the node. Okay. All right, so it's proposed for internet router applications. This is an inherently variable length key situation. The keys are the rules or filters in the table. Okay. And we're performing longest prefix match. Okay. So here, when we first looked at router tables, we talked about using binary tries. And so there you could have height going up to 32, with destination addresses being up to 32 bits long. Okay. So if you had a binary try and you were performing searches, you could have up to, I guess if your height was 32, you could have up to 32 cache misses. Then if you go through the math, you'd look at 32 cache misses and the time required to service a cache miss. There's really no way you can classify a few 100 million packets a second. Okay. So to get around that problem, you have to go to higher order tries so that you cut the height down. Now, when you go to higher order tries, and let's say you say, well, instead of 1 bit, I'm going to maybe branch on 16 bits. Okay. Well, then your node size becomes 2 to the 16 because you've got 2 to the 16 pointers in there, and the total amount of space you need for the try becomes large. So you have a trade-off between the number of levels and the total amount of space that your try needs. And to balance that trade-off more effectively, one allows to have different degree nodes instead of requiring fixed degree nodes at every level. Okay. So typically in a router table application, you might start with a specification which says I can tolerate up to, let's say, 4 cache misses per packet. That means your height is now constrained, it can only be 4. So starting with that constraint, you then want to design a try which uses the smallest amount of memory for the router table that you have. Okay. So you know all of the keys that are going to be in there, you know the target height, you want to minimize memory. What you don't know is what are the degrees of the different nodes in the try. Okay. So that's an interesting optimization problem which people have studied, and there are nice algorithms around to build optimal tries under various constraints for allowable degrees, but subject to a height limitation. Okay, so once the height limitation is given, you're kind of free to choose the strides of the nodes. If you choose the root stride to be 32 and you're looking at IP4, well, then you need only the root. Okay. There are only 32 bits in the address. Okay. So your height becomes 1. If you chose strides of 16 at the root level, 8 and 8 for the next 2 levels, you'd still cover all 32 bits. You could get away with a 3-level try. Also an example here, at the root level I've got a stride of 1, so it's got 2 children. Then at the next level, this node has a stride of 2, so it's got 4 children, and this one has a stride of 1, so it's got 2 children. Okay. In this particular organization, I'm allowing you to keep the router table filters inside the branch nodes. Okay. So a branch node not only has pointer space, it also has data space. Okay. At this node here, I'm going to keep filters that are 1 bit long. Okay. So if you had a 0 star, I would place it here. If you had a 1 star, I would place it here. The null here says I don't have a 1 star in my root table, in my router table. Okay. here I'm branching using the next 2 bits. So that will be bit 2 and bit 3 of the destination address. In this node, in addition to having these 4 pointers, I also have space for 4 filters. Okay. And these filters are necessarily of length 3. Okay. They all have to begin with 0 because I came from there. And then the other 2 bits are kind of free, so you got 4 possibilities for the other 2 bits. Okay. Here the stride is 1, so you got 2 pointers and you got 2 fields for filters. Here you branch on bit 1, and then here you're going to use the next bit after that, so that becomes bit 2. Okay. In this node, you're going to keep filters whose length is 2 bits. Okay. So 1 bit filters here. Here you have 2 bit filters, but they have to begin with a 1. Here you have 3 bit filters, but they must begin with a 0. Okay. Now, you'll notice that there's no place to put a 2 bit filter that begins with a 0. Okay. So if you had a 2 bit filter that begins with a 0, we would expand it to 2 3 bit filters. So for example, if you had a 0 1, it could be represented as a 0 1 1 and 0 1 0. Okay. So you do something called filter expansion, because when you go into multi-bit tries, you don't have nodes which can accommodate every possible length that might arise. Okay. So you go into filter expansion. As I said here, if you had 0 1, we would create a 0 1 0 filter which would occupy this spot, a 0 1 1 that would try to occupy this one. But if you already have 0 1 1, this fellow will win over the expansion of 0 1, because we're doing longest prefix matching. The longer prefix takes precedence over the shorter one. Right, in this particular try, we have nodes of different strides. Stride 1, a stride 2 node, and another stride 1. Of course, this could have been a stride 3 node. Okay. So that leads to something called a variable stride multi-bit try. As I said before, a challenging optimization problem is to select the strides of the tries, of the try nodes, so as to minimize the total memory needed by the try. Okay. The optimization problem is somewhat simpler if you make a restriction on these, on the allowable tries, which says that within a level, all of the nodes must have the same stride. Okay. Which is not true for this example, because level 2, this fellow's got a stride of 2, that fellow's got a stride of 1. But if you make that restriction, you end up with a restricted category of multi-bit tries, which are referred to as fixed stride tries. So the stride is fixed, but only on a per level basis. Okay. So that's a slightly easier optimization problem, but people know how to find the best tries that fit these requirements. All right, so you need to choose the stride. We've gone through this. If the stride is S, you have 2 to the S children. You also have space for 2 to the S prefixes. There's a rule that tells you what length prefixes get stored in a node. Short prefixes that don't fit into any of these allowable lengths get expanded to longer length prefixes. Okay. So for example, if the stride of your root is 3, and you have prefixes whose length is 3, you need to expand them to length 3. This length 2 prefix would get expanded to 0, 0, 0 and 0, 0, 1. Okay. If you already had 0, 0, 0, well then Q will get precedence over the expansion of P, because Q is a longer length prefix than P. All right, so using these rules, once you choose the strides, doesn't matter what your prefixes are, you can always fit them into your try. Okay. All right, there are plenty of other applications for tries and plenty of other variations on tries, and you really need to take a look at the readings that are there on the website. Tries are used for searching for a prefix. Okay, so if you have a bunch of keys and you're given a prefix, you want to find out what are the keys that match. Okay. A useful application of prefix search would be automatic command completion. So if you're kind of sitting in Unix and you type the first 3 letters of a command, you press the tab key, it brings everything else in, provided there is no ambiguity. Okay. It's easy to see how you can do that with tries. You kind of follow down the try. Once you reach an element node, it doesn't matter what the rest is that the user types. That's the only possibility. Tries get used to implement LZW compression, a very popular compression technique used in many commercial software. For example, if you every time you open up Adobe's Acrobat Reader, you'll see a little message down there which says implements LZW compression. Okay. A fast way to implement LZW compression is to employ tries. Another fast way to do it, of course, is to use hash tables. So depending upon whose implementation you're looking at, you might see a try implementation or a hash table implementation of LZW compression. Okay. Right, there are plenty of alternative node structures. The pictures we've been drawing and even some of the explicit statements I've made all kind of point toward representing nodes as arrays, especially if you want to have only one cache miss per level. Okay. But certainly there are other implementations people employ. You may have a chain, so you keep only the non-null pointers, chain them together. Very useful if you're dealing with very high degree tries. Instead of wasting a lot of space with nulls, you just keep the non-null information. You may even have a binary search tree of non-null pointers. You may have a hash table of non-null pointers. Okay. All right, so there's a lot more to tries than we've covered here, and the reading on the web gives you a good idea of some of the other things that people are doing with tries, some of the other implementations as well. All right, any questions? No. Okay, we'll stop then.